Hello, am I audible and is my screen visible?
Yes, sir.
Okay.
Yes, sir.
Hello everyone, welcome to this NPTEL live session for the course Introduction to Machine Learning. My name is Ayan Maiti. I'm a PhD scholar in the Department of Computer Science and Engineering at IIT Kharagpur. So this live session is for week 11 topics, and in week 11, Gaussian mixture model and expectation maximization, these two topics were taught. So we will discuss some questions on these topics, and if you have any questions or queries on these topics, you can ask me during this session. Okay, so we'll start solving the practice problems first, and after that, if you have any other questions, you can ask me. So the first question: in each of the options, the diagram contains a log likelihood function. So each of these functions are log likelihood functions, each of the four diagrams, for a particular problem, as well as the initial value of the parameter used in the example. These are the initial values of the parameters given. In which of the given scenarios will the EM algorithm, EM stands for expectation maximization, EM algorithm be able to achieve the global maximum? So you can write your answer in the chat. So if the starting point is this, whether it will be able to reach this global maximum point or not. So which of the following scenarios the EM algorithm will be able to achieve the global maximum?
So, what is log likelihood function?
Yes, the log likelihood function is probability of x given theta. X is the data points for which we are trying to find out the distribution, and theta are the parameters. So probability of x given theta is the likelihood, and if we take the log of it, it becomes log likelihood. But for the in EM algorithm, we first compute this log likelihood function, and then we try to maximize that log likelihood function, or try to find out the parameter theta for which this log likelihood will be maximized. In this case, all these functions are already log likelihood functions, so you don't need to worry about that. Uh, so you just have to find out whether, if the starting position is this initial value of theta, whether the EM algorithm will be able to find the global maximum point in each of the cases. Here the global maximum will be there. Here. So the expectation maximization algorithm works in such a way that uh, the EM algorithm might get stuck at local maximum points, and it might not be able to get out of those local maximum points and reach the global maximum. So that is one of the drawbacks of EM algorithm. So in the first diagram, so this is the initial value of the parameters, and EM algorithm will be iteratively improve the uh, theta value to reach this point, and this is a local maximum point. After that, it will not be able to traverse this to this global maximum, because once it reaches a local maximum point, it gets stuck there. So it will get stuck at this local maximum point and will not be able to uh, reach the global maximum here. So in the first case, it will not be able to find out the global maximum. In the second case, so this is the starting value of the parameters theta. So EM algorithm might search this way first or this way first. So if it goes the left hand side, it will reach this local maximum point. But if the EM algorithm searches the right hand side, it will be able to reach this global maximum point here. So we don't know which side it will search first. If it goes to the left hand side, it will reach a local maximum point here. But if it goes to the right hand side, it will reach this global maximum. So in this second scenario, it is not guaranteed that EM algorithm will be able to reach the global maximum. So this is also not happening. The third figure, C. So this is the starting point, and we see that there is no local maximum in its path from starting position to this global maximum. So there is no local maximum point, where the local maximum basically means derivative value is 0. So there is no such local maximum point we can find out from its starting position to the global maximum. So it in this scenario, it will be able to reach this global maximum point, because it is not getting stuck at any local maximum point. So in the third scenario, it will be able to find out the global maximum value, and in the fourth uh, scenario, uh, it starts at this position, and it when it reaches this position, it is a local maximum point again. So it will get stuck in this local maximum point, and it will not be able to get out of this local maximum and reach this global maximum. So this will also get stuck at this local maximum point, and this will also not be able to reach the global maximum. So there is only one correct answer, which is this option C. So in option C only, the EM algorithm will be able to achieve global maximum. So is it understandable? So moving on to the next question. So this is on Gaussian mixture models, GMM. So for the given figure, given GMM model in the figure, this is the figure. What is the value of K? So the distributions are also given. So these distributions are given. This is also the distribution given. So what is the value of K? K means the number of clusters the GMM model will find out. And in GMM model, each cluster would be a Gaussian distribution. So what is the value of K, where K is the number of clusters in the GMM model? Ansela VMs is option. Ansela VMs is 4. Okay. The correct answer would be option B 4. So from the data points and the distributions given, we can see that the GMM model finds out this as one cluster, this is another cluster, this is another cluster, and this is another cluster. So it from the contours given, we can see that the GMM model is able to find out 4 um, clusters, and each cluster is a Gaussian. So there are 4 such Gaussian like distributions given, distribution shapes we can find out. So there would be 4 clusters, so the value of k would be 4 in this GMM model. So correct answer would be 4. Now for the same figure, what is the minimum value of k dash which is not equal to k? So k, we have found out 4 in the previous question. So what will be the minimum value of k dash not equal to 4, for which you will get a very similar density estimation? From the uh, data distribution that you can see in this figure, what will be the minimum number of clusters in the GMM model that will also give a very similar density estimation? Anaga Chowgaonkar says option A, which is 3. Okay. So in this question, uh, the minimum number of clusters that will also give a very similar density distribution. So this cluster is very much separated from the other cluster, so this has to be one cluster. This is also one cluster, but these two clusters, we can actually combine these two clusters into one because they are very close to each other. And even if we uh, combine these two clusters into one cluster, the shape still remains a Gaussian shape. So we can treat these two as one if we want to minimize the number of clusters, and still overall the probability distribution remains very similar. So from that point of view, we can have this one as one cluster, this is the second cluster, this as the third cluster. So we can reduce the number of clusters, still the density estimation remains very much similar. So instead of 4, here we can reduce it to 3. So correct answer would be 3. That is the minimum number of clusters that will give a very similar density estimation. But if we try to reduce it further, it will not work that well because the distributions are, we cannot combine this whole thing as one because this is not a very Gaussian like distribution. Gaussian distributions have to be a circle or ellipse like distributions, or circle. But this distribution, if we combine these three into one, this distribution is not really represented by a Gaussian distribution, so we cannot do that. So we cannot reduce it to 2, but we can reduce it to 3 clusters. So correct answer would be 3. Now question 4, again on the same figure. So assume equal pi I are the mixing coefficients. These are called mixing coefficients. So basically pi I means fraction of elements present in the ith cluster. Assume equal pi I for each Gaussian model after the convergence as in question 2. So in question 2 we found out that k is equal to 4, that there are 4 clusters. So if we assume equal pi I, so pi I would be 0.25 for each of the clusters. I equals 1 2 3 4, 4 clusters, so pi I is 0.25 if we assume equal pi I for each Gaussian distribution for 4 clusters. What would approximately be the pi I is for the model? You will get with k dash as in question 3. So k dash we found out to be 3 in the last question. The k dash value we found out to be 3, that if we want to minimize reduce the number of clusters, there will be k dash equals 3. So instead of 4, now if we do it with k dash equals 3 number of clusters, then what will be the pi I values for this model? There are 4 pi I values. We will get pi 1, pi 2, pi 3, pi 4. In case of 4 clusters, for 3 clusters we will get pi 1, pi 2 and pi 3 mixing coefficient values for 3 clusters. So what will be the value of the pi i's of this model with 3 clusters? Answer VM's is option C. which is 0.25, 0.25, 0.5. Okay. Anyone else? So for k equals to 4, we assumed um, equal pi I values. So pi in case of k equals to 4, it would have been 0.25, 0.25, 0.25, 0.25. For 4 clusters, 4 different values, pi I values would be there. And in question 3, what we discussed is that these two these two clusters are very close to each other, and we can merge these two into one to reduce the number of clusters. So in that case, there would be 3 clusters. This is 1, this is 2, and this is 3. So the third and fourth clusters would be merged into one cluster, cluster 3. So in case of k equals 3, so there will be 3 pi I values. For the first cluster, it remains 0.5. For the second cluster, it still remains 0.5. But for the third cluster, the pi I values 0.25 and 0.25 would be summed up, because these two clusters are merged into one cluster. So it would become 0.5. So 0.25, 0.25, 0.5. So these are the 3 pi I values for the 3 clusters. So for the first 2 clusters, the mixing coefficient value remains same, 0.25. But the third and fourth clusters are merged into one cluster. So their mixing coefficient values would be added up. So 0.25 and 0.25 would be added up to form 0.5. So that would be the correct answer. So correct answer is option C, 0.25, 0.25, 0.5. Is it understandable? So now question 5. For the set of points given in orange, so these are the different points. These are the different points given in orange color. The density estimation of a GMM is given below. So the density estimation of GMM forms these contours. These contours are formed by the GMM model. So it basically means this is like one cluster, this is another cluster. So GMM finds these two Gaussian like clusters. What is the problem evident in this image or in this figure? So options are pi i's are too big. Option B says the clusters are not sampled from a Gaussian distribution. Option C is the GMM has not converged yet. Option D is there is no problem in this GMM model. Ancilla VM says option B, which is the clusters are not sampled from a Gaussian distribution. Okay. Anyone else? Prakash Chandra Boy says option C, which is the GMM has not converged yet. Okay. Sweta Lakshmi says option B, which is the clusters are not sampled from Gaussian distribution. So these are the data points. This orange dots are the data points, and as we can see that the actual clusters should have shapes like this. These clusters are not really Gaussian shaped clusters, so the data points are not actually sampled from Gaussian distributions. But if we apply GMM with two clusters, it will do a very bad job in finding out the actual clusters. So it will always, the GMM would always find out Gaussian clusters. So that's why it found out these two clusters. But we can see that the data points are not really sampled from these Gaussian distributions or Gaussian clusters. So that is the main problem, that if we try to find out two clusters from this data set or the data distribution, it will find out these two Gaussian like clusters, which are not very similar to the distribution of the data points in this 2D plane. So that is the main problem, that the clusters are not sampled from a Gaussian distribution, because the shape of the clusters are very different from the Gaussian like shapes. And a related question to this, what can be done to get a better fit? What can be done to get better clusters, basically?
Sir, sir, I have a doubt in previous question.
Yes.
So over here, the orange color, whatever is there, they are the data points, and the
Yes.
blue colored ovals which are given over here, those are the clusters found by GMM, right?
Yes. 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 Yeah. The
Okay.
orange data point,
So
orange
over
points are
here,
the actual data points, and these contours
hmm.
are basically the distribution found out by the GMM model.
Okay. So over here, the correct option is B,
Yes. Because we
not
can see that
sampled by.
the
Okay.
clusters should have shape like this. If we find out two clusters, shape should be like this,
Okay.
not Gaussian like
Okay.
shapes.
But in the question, it is given that the density estimation of GMM is given. So that means they have applied GMM only now on these data
Yes,
points.
yeah, GMM is applied, and these are the clusters found out.
Huh, huh, huh.
Hmm.
Okay, fine, sir.
So for the same figure, uh, as we found out that the data points are not really coming from Gaussian distributions, that was the problem. So what can be done to fix that? What can be done to get a better fit of the clusters? So there are four options: increase k. K is the number of clusters here. So in the previous question, k was 2, because before running the GMM model, you have to fix the value of k. That is, k is is a hyperparameter of the GMM model. So k is fixed at 2 previously. So now option A says increase k. Option B says use a better initialization. Option C says learn for more iterations. Option D says there is no problem. Himanshu Anand is asking whether only MCQs would come or code. So we don't really know whether code uh, is also coming in the exam, because the final exam questions are only prepared by the instructor, which is the professor for this course. So only he would be able to tell you, because the TAs don't have any idea about that. And these live session TAs are not involved in any of the question making. So whether it's final exam or the assignment questions. Previous years also I don't know, because we are not involved in the final exams in any way. So we don't know whether code will come, because the final exam question is only prepared by the instructor. It is not revealed to anyone else before the exam. So we don't know. You can ask in the discussion forum. So Sweta Lakshmi says option A, which is increase K. Ansila VM says option A, which is increase K. So in the previous question, we saw that K was 2. So that's why it found out these two clusters. And clusters should always be circular or elliptical in case of Gaussian distribution. So that's why the data points do not really fit with the Gaussian like clusters. But if we increase the value of K sufficiently, so we can have this as one cluster, this as one cluster, this is one cluster, this is one cluster, this is one cluster, then this one, this one, this one, this one, this one. So if we can increase the value of the number of clusters sufficiently, we can have small Gaussian distributions. So that the data would fit better. Now there are so this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So there are 10 clusters now. So you can try with different cluster values to check whether it fits the data well or not. So by increasing the number of clusters or the value of k, we can have a better fit of the data points. With k equals to 2, the Gaussian distributions do not match the data distribution or the data points in the 2D plane. But now if we increase the number of clusters, now Gaussian distributions would fit the data points really well. So this way we can have a better fit of the data points. So increase k is the correct answer here. So for example, if we use k equals to 8, So now this will be one cluster, this will be one cluster, this is one cluster, this is one cluster. So this is one, this is one, this is one, this is the final cluster. So there will be 8 clusters, 8 such clusters. So if we can increase the value of k sufficiently, it will be able to fit the data points really well. Now question 7. Given n samples x1, x2 up to xn drawn independently from an exponential distribution with unknown parameter lambda, find the MLE of lambda. MLE is maximum likelihood estimation. So MLE of lambda for exponential distribution. Exponential distribution is given as this, e to the power minus, I think it was lambda e to the power minus lambda. I think it is lambda e to the power minus lambda x. So this is the exponential distribution. So for n samples x1 to xn, what will be the maximum likelihood estimation of this parameter lambda? Yeah, this question is slightly lengthy and requires a little bit of mathematical calculations. I will show you how to calculate MLE for this exponential distribution. So this is the exponential distribution, probability of x given lambda. So this lambda value is unknown and we want to find out the maximum likelihood estimation value of this parameter lambda. So this x can take values x1, x2 up to xn. These are the samples which are given to us. So likelihood, this is the likelihood one data point, probability of x given lambda equals to lambda into e to the power minus lambda x. So the probability of the whole data set capital X given lambda would be multiplication of probability of xi given lambda, I equals 1 to n. So it will become lambda to the power n into e to the power minus summation of minus lambda summation over xi, I equals 1 to n. So this is the uh, likelihood of the whole n samples, of all the n samples. So now we will take log likelihood of that. So log of this probability of x given is, so natural log we will take. So it will be n log lambda minus lambda summation over xi, I equals 1 to n. So this is the log likelihood of these samples for exponential distribution. So let's call it L of lambda, L of lambda. Now we will take the derivative of this log likelihood L lambda with respect to lambda to find out the optimal value of lambda. So we take the derivative of this log likelihood with respect to lambda. It will be n divided by lambda minus summation over xi I equals 1 to n, and then set this derivative value to 0 to find out the optimal value of lambda. Now we can rearrange these terms, and we will find out that lambda is n divided by summation over I equals 1 to n. So this is the MLE estimation of lambda, where lambda is the unknown parameter of the exponential distribution. So that would be option C. So this way you can find out MLE estimation of any uh, parameter of any distribution given to us. So is this process understandable? So you have to first compute individual likelihood probability distribution for each of the data points xi, then multiply it for each of the samples. Here we have n samples, x1 up to xn given in the question. So you have to multiply it over I equals 1 to n. So this is what we get by multiplying it for I equals 1 to n. Then take the log likelihood, log of this probability of x given lambda, basically log likelihood. So the expression simplifies slightly so that we can compute the derivative easily. Um, Now we have to take the derivative of this log likelihood with respect to the parameter. Here the parameter is lambda. There might be multiple parameters. For example, in GMM you have Gaussian mixture model, you have mu, sigma, pi, three different kinds of parameters. So here there is only one parameter lambda, so we have to compute the derivative of this log likelihood with respect to lambda and set it to 0, and then we can find out the MLE estimation of lambda. N divided by summation over xi equals 1 to n. So in question 8, again you have to find out the MLE estimation. Now for Poisson distribution. So given n examples x1, x2, xn drawn independently from a Poisson distribution with unknown parameter lambda, find the MLE estimation of lambda. So Poisson distribution is given by e to the power minus lambda, lambda to the power x by x factorial. So this is the Poisson distribution, and it is also the the likelihood distribution for individual data points. Now you have to find out the MLE of this parameter lambda for Gaussian distribution, Poisson distribution. So I will show you the steps again. So uh, for individual data points, this is the distribution, and we have to compute the distribution for all the n given data points. There would be multiplication over I equals 1 to n e to the power minus lambda, lambda to the power xi by xi factorial. So it would give you e to the power minus n lambda, lambda to the power summation over xi I equals 1 to n divided by x1 factorial, x2 factorial up to xn factorial. Now you have to take the log likelihood of this. So that would give you minus n lambda plus summation over xi log of lambda plus this denominator, we can just simply write it as some constant because it is not dependent on the parameter lambda, and when we compute the derivative it will get cancelled out eventually. So this is the log likelihood L lambda, and if we take the derivative of this log likelihood L lambda with respect to lambda, we will get minus n plus summation over xi into 1 divided by lambda, and this is the constant, so this derivative of this would be 0, and we will set this derivative to 0, so lambda would come out to be summation over xi divided by n. So exactly the inverse of the MLE estimation for exponential distribution that we calculated in the last question.
How did we get the constant?
So this denominator x1 factorial, x2 factorial up to xn factorial. So that is not dependent on lambda, but we just care about the terms which contain lambda because eventually we will take this derivative of the log likelihood with respect to lambda. You can keep it, but it's not really required because if we take the derivative with respect to lambda, this denominator part will certainly give you 0. So we can simply represent it as c, but you can write it as minus of log of this whole thing x1 factorial, x2 factorial up to xn factorial. And if we take the derivative of this term, it certainly gives you 0 with respect to, if you compute the derivative with respect to lambda, it will certainly give you 0. So that's why we have simply represented it as some constant c. So this is the process of calculating MLE estimation for the parameters of any distribution, and we observed that this MLE estimation of lambda of Poisson distribution is exactly the inverse of the MLE estimation in the exponential distribution. So the correct answer is option D. So is there any doubt in this question? Now question 9. Suppose we have a Gaussian mixture model of 3-dimensional data points with 4 components. So 4 components basically means 4 Gaussians, or 4 clusters basically, k equals to 4. And we use a model with full covariance matrix. How many parameters are present in the model? 3-dimensional data points basically means each data point will be 3-dimensional. So each data point will be 3-dimensional. Three uh, components should be there for each data point. So you have to find out how many parameters are present in this GMM model. So parameters are mu k, which are the mean values, sigma k, which is the covariance matrix for cluster k, and pi k, which is the mixture coefficients. So mu k, sigma k, pi k, these are the parameters for one Gaussian distribution. There are 4 such Gaussian distributions. So how many total parameters should be there in the model? So for one cluster, let's say K, we have three different types of parameters: mu k, sigma k, pi k. Mu k is the mean of the data points belonging to that cluster. So if each data point is three-dimensional, so mu k would also be three-dimensional. So there will be three parameters coming from mu k. The sigma k is the covariance matrix for the cluster K. So the covariance matrix would be 3 cross 3, but the covariance matrix is symmetrical in nature. So we just need to know one triangular half of the covariance matrix. So if it is because the each data point is three dimensional, the covariance matrix would be of size uh, 3 cross 3. So one triangular half would have 3 into 3 plus 1 by 2, there would be 6. So 6 parameters coming from the Gaussian distribution, the covariance matrix sigma k, and pi k, this is the mixing coefficient. So this is one singular value, this is not a vector data point. So this is just a singular value, that is fraction of elements belonging to the cluster K, so that gives you only one parameter. So total we get 10 parameters for one cluster. So for kth cluster we have 10 parameters. Total number of clusters is 4 here. It is written that 4 components. So total number of parameters should be 10 into 4, 40. So this is how you can calculate the number of parameters present in a JMM model. So for individual um, clusters, you have to find out mu k, sigma k, pi k, and then multiply the number of parameters for one cluster by the number of parameters, number of clusters. Here it is 4, so 10 into 4, total 40 is the number of parameters present in the JMM model.
How is sigma k 6?
So sigma is the covariance matrix. Each data point is three-dimensional, so the covariance matrix would be 3 by 3, 3 cross 3. But the covariance matrix is symmetrical, so either you take the top half or the bottom half of it, bottom triangular half or top triangular half of it. So along with the diagonal elements, so that gives you total 6 parameters in this one triangle.
Okay, thank you, sir. And what about that pi k also, sir?
Pi k is the mixing coefficient. Pi k basically means the fraction of data points belonging to cluster K. So that is only a singular scalar value 1. So that it contains only one parameter.
When is it not one? At in which cases it will become?
No, it is always 1, because it simply its definition is the fraction of elements belonging to cluster K. So it is always 1. So there will be multiple such pi k values. For cluster 1 it is pi 1, for cluster 2 it is pi 2, but each pi k
And
is
why
just
is
a
it said full covariance? Why is it said full covariance matrices?
full covariance, because sometimes the half covariance is also used, but that is not really important for this question, that this whole covariance matrix is used to compute it.
No, but if it is half covariance, can you, sir, please tell what the number will be instead of that 6?
I'm also not sure. I mean, I'm not completely sure about why it says full covariance, but full covariance basically means the whole matrix it says, but it is symmetrical in nature, so you just have to take one half of it. So uh, it doesn't
That is
really
clear,
matter.
sir. Thanks.
Now, question 10. Which of the following correctly describes the differences between EM, which is expectation maximization, for mixtures of Gaussian and K-means algorithm? So both the algorithms, EM for mixture of Gaussians and K-means, are clustering algorithms. So what are the differences of these two algorithms? Multiple options may be correct here. K-means often gets stuck in a local minimum while EM tends not to. EM is better at capturing clusters of different sizes and orientations. EM is better at capturing clusters with overlaps. Multiple options may be correct. Nagachogan versus option A and B. Okay. So the correct answers are option B and C. So the first option says that K-means often get stuck in a local minimum while EM tends not to, but this is not true. Which we discussed in the very first question in this session, that expectation maximization algorithm also gets stuck at local maximum points, and it might not be able to get out of those local maximum or minimum points to reach the global maximum or minimum point. So this is also one of the drawbacks of EM algorithm, and K-means also suffers from that algorithm. So this is not really a difference between these two algorithms. Second option says EM is better at capturing clusters of different sizes and orientations, which is correct, which we also discussed in one of the questions in this live session, that if you increase the number of clusters or the value of K, you can better fit the data points. So you can use different number of clusters so that you can fit the exact data distribution, but k-means cannot do that. K-means do not find out clusters of different sizes or orientations because of its Euclidean distance measure. And the third option says that EM is better at capturing clusters with overlaps, which is correct, because the we saw that the EM for Gaussian mixture model. So the main feature of Gaussian mixture model is that the clusters can overlap and each data point can belong to multiple clusters. So that's why we have this probability of z given x for a given data point, the probability of belonging to cluster z. That is what we try to learn in Gaussian mixture model, this posterior distribution for z. So each data point can belong to multiple clusters, so clusters can overlap, which does not happen in k-means, because k-means is a hard clustering algorithm. Each data point has to belong to only one cluster. So option B and C are the correct answers. So these were the questions that I wanted to discuss in this live session. Now, if there are any other questions or queries, you can ask me. Dr. P. Pushpa is asking for the pair of distance matrix given in the pairwise distance matrix given in the previous question. Following shows the hierarchy of clusters created by complete link clustering algorithm. Give one example. Uh, I I don't have an example because we need that distance matrix for that. But I discussed an example for single link clustering algorithm in last week's live session. That was for single link clustering, but similar approach can be taken for complete link clustering algorithm also. So you can check out that last week's live session. So this is week 11, so that was week 10. In week 10's live session, I discussed one such problem where the matrix is given and you have to find out the cluster hierarchy for single link clustering algorithm. You just have to change the single link to complete link clustering. Basically the merging technique changes for the complete link, but the overall process would remain the same. And if this question was asked in the assignment, I think assignment solutions would also be provided in the uh, course web page. I don't know whether it is uploaded yet or not, but if the question was asked in the assignment, then it should be provided, I think. Are there any other questions or queries? So if there are no other questions or queries, we can end this live session now. Thank you everyone for joining. We will meet again next week.